And with the test, I usually go to the Norfolk Proctoring Center.
That shouldn't be a problem.
Um, is there any kind of instructions I should provide to them?
No. So what I'm going to do is I'll set it up tonight for all the testing centers for all my internet classes, and you just have to make sure whatever their rules are, which they'll have very specific hours. They'll say you have to have an ID. They'll say you have to arrive a certain amount of time before your appointment or stuff like that. They also say like if it's a test that's supposed to take 2 hours, you have to start 2.5 hours before their closing hours, little stuff like that. But all that'll be set up when you get there. You just need to make sure, like I said, you might have to make an appointment, but other than that, shouldn't be anything. So hopefully they'll know it all. All right. Well, it looks like I've got enough people here. I got seven of you folks in here, and we have that it's 5:22. When we last met, I'm just looking at my notes on this a second ago. Let me double check that now. I got sidetracked and ended up forgetting to do it. Oh, here it is. I was just checking the notes from the last time we met, and if I remember correctly, we had worked through air resistance. Oh yeah, and I'd set up a position vector. So I want to start off with that. Actually, I want to start off with solving a couple problems, then we'll go to that position vector one that was about rotational motion or circular motion that we're talking about in this chapter. So let me start off with my example. I've got two examples written up, and we're going to start with those. Who was it? Was that John I was just talking to, or was it Zach? Y'all hear me?
We were talking before class started.
Okay, was that you, Daniel? Daniel, gotcha. Okay, so Daniel had a question, and it's a good question. So I'm definitely going to solve it at the end of class. It's one where there's a large box with like sitting on on the ground or floor. There's a rope tied to it. It goes around a pulley, and then the rope comes off the pulley and goes to a smaller box sitting on top of the big box. And it does have friction, so that's a really good problem. I like that one, but it's pretty straightforward. But if you miss one of the forces, you're toast. So I definitely want to work that, but it's not in chapters one, two, three, and four. And since you guys have a test this week in chapters one, two, three, and four, I want to make sure I get through chapter four stuff before I go ahead and press on with that. So I'll do it at the end of class. If you end up having to leave because of lab, don't worry, I'll finish it anyways. It'll be recorded. And also, if you have to go and you don't get to, interact with me while I'm solving it, you can feel free to just send me a text message and I'll set up a Zoom session for tomorrow morning, or I have various times. Tomorrow I'm already doing a Zoom at noon, which I do every Tuesday. But by 12:30 I'm finished introducing the lab, so that's an open office hour starting at 12:30, so anybody can log in there as well. Anybody else have any questions before we get started? So try to remind me, Daniel, if I don't remember. But like I said, if you have to split because you got lab, I understand that. I will tell you guys too, just to remind you, in case y'all are doing your lab thing right after this. I haven't got the impression that that's what y'all are doing. I think y'all do it on Wednesdays maybe, but I might be just misremembering. But the main thing is, if you have lab right after this. We have computers at campus on our hall specifically that you guys could use to do the Zoom meetings. That way you wouldn't have to like rush out and then rush to the campus and then go to your lab. You could do it if you're already on campus. Obviously, if someone's coming from work, they might not be able to afford that time to do that. But if you need to, just let me know and I'll make sure I can get you somewhere. So, any questions? All right. Well, we now got nine people in here. I want you to go ahead and chat me your first and last name. I'm going to use that as roll, and I'm going to go ahead and share my screen with you guys to work some problems related to friction. So let's get crack-a-lacking. I don't know where that crack-a-lacking came from, but it's some cheesy movie, I'm sure. Because, of course, the best series in the history of television is clearly Trailer Park Boys. So I need y'all to get caught up on that series so that I can make random jokes that make me laugh. All right, here we go. Example one. It says a 15-kilogram box is pulled along a level floor by a force of 60 newtons applied at 36.9 degrees above horizontal. If the kinetic friction is 0.30, what will be the acceleration of the box? So that's a pretty straightforward problem. I'm going to work it like this. I write out solution, and this is normally just so I can show you where the solution starts. I don't have to do it so much. It's more important that I do this in my lectures as opposed to my online classes because here I do it with clearly a different color writing, so that normally is enough for it. But what we're using, of course, is the summation of the forces is equal to mass times acceleration, and we'll do that in the x direction as well as the summation forces in the y direction is equal to mass times acceleration in the y direction. We're also going to use the static friction force is equal to mu static times the normal force. I usually write that as just N. I'm writing it as F sub N this time because it looks like a lot of my students are doing that more. There's also another one that's going to come up with example two, so I'm going to put that here, and that's, oops, I wrote them exactly backwards. So since that's static, I'll put this like that, and since this is kinetic, I say exactly equal to mu kinetic times the normal force. So that's what we'll be using. My diagram looks like this. I'm going to draw a coordinate system just because once we have a coordinate system, we can decide which vectors point in a negative direction or a positive direction because the vectorness of it, once you reduce it to one dimension, the vectorness of it, meaning its direction and magnitude, the magnitude is just the numerical value, but the direction is the positive or the minus within one dimension. So if I put this y-axis pointing up, which is what that y indicates up there, and this x-axis pointing right, which is what the x being there points out. So this means my directions are x is positive to the right, negative to the left, y is positive up, and negative down. I'm going to imagine the box as a point particle, and that is m equals 15.0 kilograms. Now, I have a force in the downward direction that happens to be parallel to an x or y axis, so I'm going to use colors with it. And in fact, that force is the weight, and the weight W is equal to m times g, which in this case is going to be 147.0 newtons because 15 times 9.8 gives you 147. That's one of the forces. We also have that a normal force must be acting because otherwise, this one force in the downward direction would cause it to dig into whatever surface it's sitting on. The normal force, of course, is pointing in the upward direction, so I'm going to make that a positive force, obviously, and that force is F sub n, which we need if we're going to use either of those friction formulas. Now, in addition to that, there's obviously some friction on it. The box is being pulled along a level floor by force of 60 newtons applied at 36.9 degrees. And what I can do with that is that's not along an x or y axis. So I'm just going to draw it as a black vector. And then I'll make the components whatever colors they need to be so that they're pointing in the specific direction that corresponds to that color. So this right here is 36.9 degrees, and this right here is 60.0 newtons. What we can see now is that the x component is to the right, so it's a positive, and the y component is up, so that's a positive as well. So if I called this 60 Newton force just plain F, then this would be F sub Y. and this would be F sub x. And since I have vector symbols on them, I could specifically write them like that. Now, the big thing that I want to do is I want to say that sine of 36.9 degrees, again, we're imagining that we're still not taking off our training wheels, but in so doing, we just automatically write down what the sine is and then solve it for the component that we can get. And then we write down cosine and solve that for the component. So that's what I'm doing here. Sine is opposite over hypotenuse. So that is actually Fy over 60.0 newtons. That means F sub y. And notice I'm forcing this. I'm writing this positive symbol here, and I'm forcing it specifically because I never put in negative angles or weird stuff like that. I also never put in angles bigger than 90 degrees because I want my logic and understanding of how the vector is drawn out to tell me whether or not the components are positive or negative. So for instance, you probably already know this in this case, but for instance, the sine of 36.9 degrees is 0.600. So if I multiply 0.600 times 60, zero point 0 newtons to 3 sig figs, that gives me 36.025. So that's 2 extra sig figs, and that's newtons. And now I can write out cosine of 36.9 degrees, and that is adjacent over hypotenuse, so that's F sub x over 60.0 newtons. So again, I'm forcing this by writing F sub x is equal to positive, and now what I'm going to do is take 60.0 and multiply it by the cosine of 36.9 degrees, which should be zero point 0.4. Yeah, I think so. Anyways, you're going to get 47.981, and that gives me 2 extra sig figs, just like I did before. Now, finally, the last force I have is going to be a friction force, and just out of convenience, I'm going to draw it pointing to the left, which it actually has to be pointing to the left because I'm imagining pulling it to the right. But normally I put the arrowhead, or a lot of times I'll put the arrowhead actually on the mass. This time I put it on the tail. But actually, in looking at it, it looks like every one of them I did the opposite way. I'm used to putting them the other way, but evidently I didn't done none of them that way this time. All right, so now that we have all that written, I can now realize that this box will be pulled horizontally across the surface like this. There is a component pulling up on it, but we are not expecting that to cause the center of mass of the box to lift any. So in some sense, you can think that the y component, or the y ordinate, the actual height of, let's say, the center of mass above the ground, that's not going to change at all. And since that's not changing, its derivative must be zero. So the derivative of y with respect to time is zero. And the derivative of y with respect to time is also the velocity in the y direction. So the velocity in the y direction is zero. Since the velocity in the y direction is zero, and you wait a couple seconds and it's still zero, that means the acceleration in the y direction is zero. So I can now write the summation of the forces in the y direction is equal to mass times acceleration in the y direction. And I'm just going to put a zero right there for the acceleration in the y direction. Now, when I do this, I can go ahead and say that the forces I have acting in the y direction are the normal force, which I started to write as plain N like I normally do. So I caught that. But there's also F sub y, which we just discovered was 36.025, and that's a positive direction. So I'm going to say plus 36.025 newtons. And then there's a force acting in the negative y direction. So that one's plus negative 147.0 newtons. And all of that is equal to zero. So all this one allows me to do is to figure out the normal force, which is clearly 147, because when it comes to the right hand side, it'll be positive. minus 36.025, and that gives me 110.975. Now notice the 36.025 was only good to one decimal place. The 147 was good to no decimal places. So technically speaking, the 9, the 7, the 5 are not significant figures, but we still managed to hold on to three of them. Now that I have the normal force, I can use that to actually calculate what my friction force is using the formula above, which we're talking kinetic here. So it's this one. Okay. And we know mu is zero point 0.3. So now I'm going to write the summation of the forces in the x direction is equal to mass times acceleration in the x direction. Now, in this case, the acceleration in the x direction is the only acceleration we're dealing with, so I'm not going to subscript it x. I'm just going to call it a. And not only that, that's the thing we're solving for, so we can just work it out accordingly. So the forces in the x direction you can see are that force and this force. This one's obviously in the positive direction. This one's obviously in the negative direction. You're adding all of them, but like I said, some of them are positive and negative, so you have to take that into account. The positive one is F sub x, and we said that one was 47.981 newtons. And that one was a positive, so I'll put a positive by here. And then we're going to add to it any other forces, which in this case is supposed to be mu static times the normal force. So again, I'm pointing to this formula right here where mu k is zero point 0.3 and the normal force is this guy. And notice it's in the negative direction, so I'm going to put a negative sign there. Again, I'm forcing that because it's pointing in the negative direction. But in this case, I'm going to say 0.30 because that's the static, or excuse me, the kinetic coefficient of friction times the normal force, which is 110.975 newtons. And then all that is equal to the mass of the box, which is 15.0 kilograms, times the acceleration in the x direction, which is the only acceleration we're dealing with. So that's the A that I got to solve for. As I go to solve for it, what I'm going to do is take 47.981 plus a negative is the same thing as minus. Now I'm going to say parentheses zero point 0.3 times 110.975 close parentheses, and that gives me a total force of 14.6885. I'm writing like all the numbers there. Now, what that is just this part from here to here. That's what's there. Okay. So all I have to do is divide both sides by 15.0 kilograms, and that'll give me my answer. So I'm going to put under that 15.0 kilograms and divided by 15. Now, when I did that addition subtraction stuff, it turned out that the 47.981 was good to one sig fig, or excuse me, to one decimal place. The zero point 0.3 times 110.975, that had two sig figs, so that was not good to even one decimal place. So in fact, I have to say those two numbers make the 6, the 8, and the 5 not significant figures. So I'm dividing 2 sig figs by 3 sig figs, and that gives me 14.6885 divided by 15 is 0.9792 meters per second every second. Remember, this unit on top was a Newton. So that is our acceleration. And of course, we don't have this digit or that digit as sig figs. So our acceleration is going to be 0.98. Anybody have any questions on that one? All right. So one of the big things that might make this a little confusing for students in general is this equation. I just want to remind you, all it's really saying is that the static friction force will be basically whatever it needs to be up to some maximum value. So if you supply a force that's bigger than that maximum value, then it has to give up. But if you apply any force smaller than or equal to that maximum value, which is mu static times the normal force, then that's what the static friction force is going to be. Okay, so that's why it's written as less than or equal to. So I wanted to follow this question up with example two. It says if the static coefficient of friction in example one above is 0.40, will the 60 Newton force be sufficient to start it moving? So if you look at the uh, problem that we just worked, we've got sort of what we need to solve this problem. We already worked out what the normal force is. Nothing should change about the normal force. The force applied, the 60 newtons, that still breaks into x and y components just like we expect. The friction force, basically, we don't have a computation for that yet because we use the formula for kinetic coefficient of friction, and we're trying to figure out whether it exceeds the static value of friction. So that's all we've got to do is test that. So what I know is that the normal force is equal to 110.975 newtons, and therefore the maximum static friction, F sub S max, is equal to 0.40 times 110.975 newtons. Again, the 9, the 7, the 5 are not significant figures. I'm sorry I put so much emphasis on this. I just want my students to know the rules so that they can match ideally what the homework system does, even though I don't care about the sig figs that much. So, anyways, zero point 0.4 times 110.975 gives me 44.39 newtons. And that really should only be two sig figs, so the 3 and the 9 are not significant figures, but that's the maximum force the friction force can be. What we discovered, though, was that the X component of the 60 Newton force was in fact 47.981. So F sub X is equal to 47.981 newtons. And of course, the 8 and the 1 were not significant, but that is greater than the static friction max. So, yes, it is sufficient. Does that make sense to everyone? Anybody have any questions on that one? Any questions on anything else? All right. Now that we've done that, I want to go ahead and show you what I'd asked you to work on yourself. And so I'm going to go through this a little quickly as opposed to the ideal scenario would be that I walk you through it and I'd ask you questions and you'd answer me. And if everybody did that exercise as I asked them to do, then that would go pretty quickly. But in general, I know that probably I haven't had a chance. So I'm just going to go with it as if we didn't. What I suggested was for you guys to consider the vector function r. That's going to be r specifically of t. And the one I told you it would be was r times cosine omega t. And I'm going to write out what that omega is in a second, times I hat plus r times the sine of omega t times j hat. Now, omega is equal to 2 pi times the frequency, but it's also 2 pi over the period, t. Okay, so F is equal to the frequency, which equals the number of circles slash cycles. In this case, I'm literally making individual circles. That's why I wrote circles. So it's the number of cycles or circles completed in 1.00 second. So that's what the frequency is defined as. T, which is also 1 over the frequency, is equal to the period. And that equals the time required to complete one circle slash cycle. Later, we're going to cover more general things as opposed to things that are just going in circles, in which case we'll refer to it as a cycle. Like you might imagine a mass at the equilibrium point of a spring, and the spring has, or the thing hanging from the spring has been given a little push downward. So it'll go down, reach its lowest point, and then turn around, go back through the equilibrium, reach its highest point, and then turn around and go back to equilibrium. That's one whole cycle. Notice I went from equilibrium to maximum elongation to equilibrium to maximum compression back to equilibrium again. That second equilibrium is one whole cycle. So that's what you need to have some understanding of when you're using this. Now, that means I can rewrite this R of t. Well, actually, I can rewrite this R of t as R cosine 2 pi over the period times t I hat plus R sine 2 pi over the period times t j hat. Interestingly enough, if you actually tried to calculate the magnitude of this, and this is something you should give it a try, okay, you're just going to use the Pythagorean theorem, and what you'll get is the magnitude is just r. So try that yourself. Now, if you were to actually plot this, what you'd find is that t equals 0 seconds. This is going to be setting, this vector is going to be a vector r units long, and it's going to point from the origin to x equals r. And if you go to a quarter of a period, in other words, you let t equal capital T over 4, then what you'll get is the vector again has a length of r, but this time it'll be pointing straight up along the y-axis. And then if you go to t equals capital T over 2, then you're going to find again a vector of length r, but this time it's laying to the left and points to y equals, or excuse me, x equals negative r. And then if you do t equals 3/4 of capital T, you'll get that it's r units long again, but this time it's pointing down along the negative y-axis, a distance r. And then if you go all the way to capital T, then you'll get the original point, which was at x equals r. So what you're seeing is a vector that at t equals 0 points to the right, which is the positive x-axis direction, and is a distance r away. At t over 8, it's about 40, it's exactly 45 degrees up and pointing that way. At t equals t over 4, it's pointing like that. At 3t over 8, it's pointing like that. At 4t over 8, which is t over 2, it's pointing like this, and then this, and then this, and this. So you can see it's really just a vector r rotating around in a counterclockwise direction. Okay. That's what r of t represents. So I'm going to draw that really quickly just to let you know what it should look like. I'm going to attempt to do it roughly in the center of the page. Okay. And that's 1, 2, 3, 4, 5. 1, 2, 3. I think I'll do it right about here. Okay. I'm going to assume the circle has a radius of 4. So I'm going to put a dot here. Oops. Actually, I got to put it in regular drawing. I got to put a dot here. I got to put a dot here, here, and here. And what I was just pointing to was this is r of 0. And in fact, this quantity is r. If we go up to here, this is r of t over 4. This is r of t over 2. And this one is r of 3t over 4. And in fact, like I said, I asked you guys to do increments of an eighth of the period t, and that'll give you the 45-degree angles as well. Uh, when you come back, though, it'll be r of the whole period is also the same answer. So that's what these vectors are. And let's see if I can actually draw it correctly. I'm going to draw it in black. There you go. Not too bad. Let's see if I can move this just a little bit. Looks like that's pretty good. Okay, so that's really the motion that we're talking about. It's actually going around in a counterclockwise circle like this. And at each point, the R, or excuse me, at each point in time, the R points to the location of whatever object this is describing, which basically is just supposed to be describing the path that the object's following. Now that we have that, I want you to recall that V was dx dt, but once we started studying projectile motion, we discovered that V sub y was equal to dy dt, and V sub x was equal to dx dt. So hopefully from that, you can automatically see that V in vector form is just going to be dr dt. So when I go to take the derivative, the r is a constant. We're taking the derivative with respect to time. So really all I got to do is take the derivative of cosine, and then according to the chain rule, I've got to take the derivative of the argument of cosine with respect to time. So you notice that the derivative of cosine is negative sine. So I'm going to get a negative, and then it's going to become the r that I already had, plus I got to take the derivative of 2 pi over t times little t. The derivative of that with respect to little t is 2 pi over t, and then I have r sine 2 pi over t times little t I hat. Now, when I take the derivative of the next term, that's the derivative of sine, which gives me positive cosine, but I still have to do the chain rule stuff, so that's still going to be 2 pi over t times r times this time it'll be the cosine of 2 pi over t times lowercase t j hat. Now, I will remind you that it's perfectly acceptable to realize that this 2 pi over t is omega, and so is this one. Okay, so that might be kind of helpful. In fact, I want to go ahead and compute what the magnitude of v is, and that's equal to the square root of the squares of the individual terms. Notice one's in the I hat direction and the other one's in the j hat direction, so they're clearly 90-degree angles, which means the Pythagorean theorem applies. So what I'm going to do, instead of calling it 2 pi over t, which is ugly, I'm going to call it omega. And of course, it's negative omega, and I got to square it. So negative omega times negative omega just makes omega squared, and then times r squared, and then times sine squared of the argument, plus again omega squared r squared cosine squared of the argument. But notice it has a common factor of omega squared r squared. So I can go ahead and pull those out in front and just write it as omega r, and then times the square root of sine squared plus cosine squared. But remember, that's just equal to 1 because they have the same arguments. So that's just 1. So we figured out that, in fact, the velocity also has a constant magnitude. And we could say it basically like this: V tangential is equal to R times omega. Now, you might take issue with me and suggest that we have no reason to believe that it's tangential to it. But what I can show you is that if we take that first term and we set it at t equals 0, so v of t equals 0, what that means is I'm plugging in a 0 right there, and that means this whole term is going to be 0. But putting this one in 0, that's going to make this 1, and therefore the magnitude is just going to be mega r, and it's going to point in the upward direction. So we can conclude that the velocity at t equals 0 points upward. If we do it at t over 4, you're going to find out that it points this way. And I drew that about 2 squares, so I don't know that 2 squares is the right scale, but if I say it is, then it has to be, because I could be using a different scale for my red vectors than I use for my blue vectors. So the fact that they're all the same is good. So there's that one. There's that one. And this is V of 0, but it also turns out to be V of t. And this one, of course, is V of t over 4. And this one's V of t over 2. And this one is V of 3t over 4, like that. Okay? So you can see that this velocity is really tangential to the curve. So that's why I wrote V tan is equal to R omega. Anybody have any questions on that? All right, so now let's compute the acceleration using the same sort of reasoning we did before. The acceleration should be equal to dv over dt. So I'm going to take the derivative of that same function. Notice the first term is a derivative of sine, which gives me cosine. So the negative is just going to stay there, but it's going to cough up another w, or excuse me, another omega, because I have to take the derivative of sine, which is cosine, and then I have to take the derivative of omega t with respect to t. So instead of just having negative omega, now I'm going to have negative omega squared times r times cosine of, and I'll write it as omega t just to make it easier to write, I hat. Now, this other one is a derivative of cosine. This time, the cosine, when you take a derivative of cosine, you get negative sine. So now all of a sudden, I've got a negative again, and I have to get another omega. So it's going to be omega squared r, just like I had on the previous term. And now instead of cosine, it's sine omega t, and that's in the j hat direction. Now, if you wish to plot that one, if you try t equals 0, well, we don't even have to jump there. Just notice that this looks exactly like, let's say, negative omega squared times r cosine omega t I hat plus r sine omega t j hat. So you see that it's literally negative omega squared times r of t. So the way we can graph it is I'm just going to write it and say it's 1.5 squares long. That'll be the magnitude I choose. And it always points radially inward, whereas the r pointed radially outward. I'm saying the word radial, radial, like you've heard of tires. So in this case, this is r of 0, or excuse me, oops, it's actually a of 0, and you'll find out also it's a of t. And this one is a of t over 4. This one's a of t over 2. And this one's a of 3t over 4, like that. So now what we've realized is that the acceleration required to go in a circle evidently is a center seeking acceleration. In fact, it's called centripetal, which means basically going towards the center. Okay. And its magnitude, you can see, is equal to magnitude of A. You can automatically see it here. It's omega squared r. But if you wanted to use your Pythagorean theorem, you'd see that that is the case. But you could also realize that this expression for v tan equals r omega tells us omega is equal to v tan over r. So I can really replace the omega squared with v tangent squared over r squared, and I'd end up getting v tangent squared over r. And in fact, that is two different versions of the formula for a sub c, which is called the centripetal acceleration. Okay. Any questions on that? So all of that was really one to show you how to deal with vector functions in terms of taking derivatives, integrals, that sort of thing. Two, to see that the centripetal acceleration required to maintain a circular orbit is in fact v squared over r, or omega squared r would work as well, and that it points radially inward and it's in the same plane as the velocities and the radius vectors. Okay, so the vectors that point to where the particle are in the same plane as the vectors that are the velocity, and that is the acceleration. So, any questions on that? All right. So now that we have that, you might want to say example 3. The moon completes one revolution about the Earth every 27.3 days. Oops. I just made my I into a T because it's so much easier than writing two separate letters. So it is completing, I should say, a nearly circular orbit whose radius is 384,000 kilometers. What is its centripetal acceleration? Notice I'm not saying centrifugal. The FUGAL is not a real force. It's what we call a fictitious force in physics. So hopefully that's one of the things you'll leave this physics course knowing that there's no such thing as centrifugal force. In fact, it's actually uh, if you try to write if you try to write a position vector like the R that I just did right here, if you did something like that in a coordinate system that was rotating, and you computed the acceleration by realizing that the rotating coordinate system makes your I hats, j hats, and k hats rotate, what will turn out is you'll get extra terms in the acceleration side on F equals ma that when pulled over to the left side they look like forces, and but they're not. They're these fictitious forces. So that's really where that comes from. That's exactly where the formulas that you'll learn in your dynamics class comes from, and you can ask me about that when y'all get to them if you so desire. Anybody have any questions about the problem we're getting ready to solve now? Okay, so the solution is going to involve uh, centripetal acceleration is equal to v squared over r. R, it's equal to omega squared r. Either one of those are fine. In class today, I did it using the omega squared r. I think I'm going to do the same thing because I want you guys to understand what this omega is. Omega, another word for it or another name for it, is the rotational velocity or the angular velocity is another term for it. You could also call it the well, I'll tell you this. We often use units because these are the best ones to use for it, but we use units of radians per second for omega. So that's another way of thinking about it as compared to like RPMs, which is another version of omega, but that's in revolutions per minute. And it's pretty straightforward in terms of circular and cyclic motion, what these things are. But the more you think about them, the better off you'll be. So we're going to go ahead and calculate that. What I'm going to tell you is that when it says the moon completes one revolution about the Earth every 27.3 days, that means that T, which is the period of rotation, or revolution in this case, notice I'm saying revolution, which is actually different from rotation. Revolution is something you do around another body. Rotation is something you do around an axis through your body usually. Okay, so t, which is the period of revolution, is actually equal to 27.3 days, which obviously, if we're using the proper units, we can't use days. Okay. So what I also know is that omega is equal to 2 pi over the period because that's what we used when I was doing the derivation for the angular acceleration. Remember, I called omega 2 pi over the period. So you could use that. You could also use 2 pi times the frequency. Either one of those would be acceptable, but the stuff they gave us really lends itself to using the period idea because the period of revolution is the amount of time it takes for when you look up in the sky and you see the moon, and let's say it's right next to a star. Let's say specifically it's right next to the star Sirius, okay, which is also called the dog star. It's part of Canis Major. But because the dog star is so far away from us, when the moon completes one 360-degree revolution around us, then we should be able to look towards it and see Sirius in that same spot again. That way we know we're looking in the same direction that we did 27.3 days ago. So it's literally the distance or the time period between, let's say, the moon being, 2 arc seconds to the left of Sirius. And if you come back the next time that the moon is 2 arc seconds to the left of Sirius, then you know the time period would be the period of revolution. So now that I use that, I can say omega is equal to 2 pi divided by 27.3 days. And then you've got to multiply that by 24 hours per day. And then you got to multiply that by 1 hour equals 3,600 seconds. So if I do all this, then I can say 2 times 3.14159 divided by parentheses 27.3 times 24 times 3,600, close parentheses. That gives me 0.00000026638, and that's in radians per second. Okay. Notice I wrote that as radians per second. That's what it automatically comes out to when you work it out this way. Uh, of course, we only had 3 sig figs in there, so this and this is not 3 sig figs. But I wanted you to notice the way I wrote this. If you ever turn in anything with long strings of numbers that are all the same, like 1111 or 0000 or 9999, always put them in little pods of 3 like this so it's easy for us to count. And it doesn't matter if you mix it up. Maybe you group these two and then you group these 3. That's fine too. Long as I can see what you've grouped in pods of 3, that'll be fine. Now that I have omega, I can go ahead and calculate what AC is. So the centripetal acceleration is supposed to be omega squared r. And of course, we can't use r in kilometers. We've got to use it in meters. So I'm going to say 2.6638 times 10 to the negative 1, 2, 3, 4, 5, 6, 10 to the negative 6 radians per second squared times 3.84. Notice it's pretty much only 3 sig figs. It's what your book would call ambiguous, but I'm going to treat it as if it's 3 sig figs. And you'll notice it's 3.84 times 10 to the fifth, but that's in kilometers. So I'm going to say 3.84 times 10 to the eighth because I need it in meters. So if I take this number, the 2.6638 times 10 to the negative 6, and I square it, and then I multiply that by 3.84 times 10 to the eighth, I get the angular acceleration or the centripetal acceleration AC equals 0.00272, and then let's say 4 and then 8. We really only have rights to 3 sig figs, so technically only the 272 are correct, and this comes out in meters per second every second. Anybody have any questions on that one? Everybody should have their calculator out. So, assuming you do, and if you don't, go ahead and get it out now. What I'd like you to do is multiply that number times 3,600 and see what you get. I suspect you're going to get something like, and the reason why is this is exactly the calculation that Isaac Newton did that allowed him to discover the uh, formulation of the equation for gravity. Basically, what he did, according to his own writing in his Principia, he looked up in his his parents' orchard or his mother's orchard. She had an apple orchard, and he looked up and he saw an apple, and then in the distance he saw the moon, and he said that he realized how similar they were, and what he meant by that is the moon, according to Galileo's law of inertia, which later becomes Newton's first law of motion. According to that, the moon should continue going at a constant velocity in a set direction, yet it always turns so that it stays the same distance away from the center of our Earth, roughly. Okay. Well, he was saying if the apple and the moon are alike, what he means is that eventually that apple is going to get so juicy and succulent that it's so heavy, gravity will pull on it with such a large force that the stem will break and it'll fall to the ground. And he knows the acceleration that that apple would experience is about 9.8 meters per second every second. He similarly says, well, just like that, that force of whatever it is that's pulling the apple towards the ground, what if that's the same force that's pulling the moon out of its tendency to go in a straight line at a constant velocity? Well, he said, if that's the case, then I'd expect it to sort of behave just like the gravitational force that I think is causing the apple to fall. And he realized the apple was 1 Earth radius from the center of the Earth, whereas the moon was 60 Earth radii from the center of the Earth. So he had been studying light, and he learned that light actually falls off in brightness as a function of distance squared. So, for instance, the brightness that you have 1 meter away from a light bulb is, in fact, 4 times brighter than 2 meters from a light bulb, and 9 times brighter than 3 meters from a light bulb, and 16 times brighter than 4 meters from a light bulb, so on and so forth. So his reasoning was, well, if the acceleration at the surface of the Earth is 9.80, and that's at 1 Earth radii, then at 60 Earth radii, it should be 9.80 divided by 3,600. And lo and behold, if you take 9.80 and divide it by 3,600, you'll get 0.00272. So at that instant, Newton is the only person on planet Earth that understands exactly why the moon orbits the Earth and why the Earth and its, satellite orbits the sun, and why Mercury orbits the sun, and why the moons of Jupiter orbit Jupiter, so on and so forth. So it's a kind of big deal. Another interesting way, though, is this, and I need to show you this. So an alternative solution. And I'm not really needing to show you a whole different solution, but I need you to think of another way of doing it. So we know that A centripetal is equal to V squared over R. So I would like you to think, given that velocity is equal to distance divided by time, do you have any idea what distance the moon must travel in that 27.3 days? I'm not asking for a number, I'm asking for like a concept or a name for the specific distance or length or whatever. Anybody have an idea on that? Let me check my chat to see if, oh, a lot of people chat. Oh, that's all their names. Cool. Anybody come up with a answer for that? Velocity of the moon. We're going to assume it's going in a circle. What we just saw was, at least when I gave you a R that gave us circular motion, we found that the R vector had a fixed magnitude, and then the V velocity vector had a fixed magnitude, and that the acceleration A had a fixed magnitude. So it seems, at least, that if something goes in a circular orbit, it must have a constant speed. And what I'm saying is, since it has a constant speed, it should be some distance divided by time. And Brianna said a full revolution. Yes. Uh, when you say a full revolution, what kind of path are we following? What's the shape of that path? It would normally be an ellipse, but in this case, we're going on the assumption it is different. It is a little slightly different than an exact circle, but we're going on the assumption that it's going to be circular. Yeah, exactly. Good job, Brianna. So, what's the distance around a circle called? Yep. So it's the circumference divided by the period. So that's a big thing for you to understand, because this gives you a whole nother way of solving the problem. Plus, you can discover exactly how fast the moon is going, which is, the kind of fact that it would be helpful to know when you go to think about things like, oh, okay, I see the moon up there. It looks really pretty, and it looks like it moved almost no distance whatsoever in the last hour. I wonder how fast it's going. We're going to find out that. So we're going to go ahead and calculate the velocity. It is, since we now know it's circumference divided by period, it's going to be 2 times pi times r divided by that 27.3 days. But again, the 27.3 days is going to be multiplied by 24 hours per day and by 3,600 seconds per hour, like that. And then this R is 3.84 times 10 to the 8th meters. So now I can say 2 times 3.14159 times 3.84 times 10 to the 8th. Now I'm going to divide that by parentheses 27.3 times 24 times 3,600, close parentheses, and that gives me 1,022.90 meters per second, which, by the way, is 2,300 miles per hour. So that's pretty fast, 2,300 miles per hour. Of course, we really only had three sig figs, so the 2, the 9, and the 0 are not sigs. Now we can write A centripetal is equal to 1,022.90 meters per second. That quantity's got to be squared, divided by 3.84 times 10 to the 8th meters. And when you do that, you can get 1,022.90 squared. And now I'm going to divide that by 3.84 times 10 to the 8th. And that gives me, lo and behold, exactly the same number. and then 8, 1. So you can see that. All right. So keep that in mind if you're ever talking about an orbit that's elliptical, at least regarding the orbits of our planets, it turns out they're really, really close to purely circular. So it's not a bad approximation in most cases to assume they're circles. And whenever you need the velocity or the acceleration for a circle, you can use that the velocity is going to be 2 pi r over the period. And then you can use that the acceleration is going to be that for a circle. So it's v squared over r. So any questions on that one? All right. Here's another problem. This one's going to be example 4. I think that's what it is. Yep, it is. Okay. So example 4. A car of mass m is traversing a banked curve of radius r. At what angle theta should the curve be banked? Should the curve be banked so that friction is not required? Okay, so we're going to bank it at an angle where we know that it'll make the turn just as if it's going the speed v. Uh, what angle theta should the curve be banked so that the friction is not required at a velocity v? Okay, think that should have been think with an I, not think with a A. Think about the negative consequences. That's just a reminder for us. Okay, so solution. What we know is we're going to use the summation of forces in the x direction equals mass times acceleration in the x direction. The summation forces in the y direction equals mass times acceleration in the y direction. And we're going to use that the centripetal acceleration is equal to v squared over r. R is equal to omega squared r, whichever one. Okay. I'm going to go ahead and draw a coordinate system. Now, I will tell you, this is the only time that I do this. It turns out, like every other time I try to solve any problem that involves an inclined plane, you're almost always better served by tilting the axis so that the x-axis would be parallel to the tilted plane and the y-axis would be perpendicular to that tilted plane. But in this case, you do not. Okay, so just keep that in mind. So what I'm going to do is I'm going to draw a vertical y-axis and a horizontal x-axis like that. And this is my x-axis. This is my y-axis. Now, what's going on here is we actually have a curve banked at an angle theta like that. Now, the car, of course, would be sitting something like this. Okay. And what we're saying is the radius of curvature, uh, the center of it is way off to the right. Okay. So that's what we're trying to picture here. I'm going to treat this as if it's just a point particle of mass m, and now I'm going to go about drawing all the forces that are acting on it. One force acting on the car is the car's weight, and that one actually already aligns along the negative y-axis. So I'm going to draw it like this and realize that it's equal to m times g, right? Now, there's also a force that's going to be acting perpendicular to the road. So it'll be at a 90-degree angle to the road, and that force is what I call the normal force. Okay. Now, in order for us to actually make sense of that normal force, I have to convert it to the x and y axes components so that we can make some sense out of it. So I'm going to do that now. It turns out if you try to walk from the tail of the normal force right here to the head right here, you have to go up and to the right. So I can say already that the x component and the y component of these are both going to be positive. So I'll use blue. And this is F normal sub X. And this is F normal sub Y. Now, here's the hard part. What I got to realize here is this forms a right triangle. So this angle theta means this angle is 90 minus theta. Since that's 90 minus theta, this one has to be theta. But since this one has to be theta, this one has to be 90 minus theta. But since this one has to be 90 minus theta, then this one has to be theta. So that's a key skill that you got to be able to figure out. Make sure you can always work out where the theta ends up in these types of things. And what we're going to do now is we can go ahead and write out our trig functions. We can say the sine of theta is opposite over hypotenuse, which is the Fn sub x over just plain Fn. And that means Fn sub x, which points in the positive direction. So I'm forcing that sign to be on it. That's going to be equal to F normal times the sine of theta. Similarly, we can calculate the cosine theta as adjacent over hypotenuse. That is Fn sub y over Fn. That also points in the positive direction, so I'm going to say Fn sub y is equal to positive Fn times cosine theta. So now we have those forces all in terms of the x and y components. I'm going to go ahead and write out the summation of the forces in the y direction is equal to mass times acceleration in the y direction. Now, if this was, for instance, the Daytona Speedway or something like that, that angle steep pretty is angled pretty steep. What we're trying to shoot for here is a car that can stay the same height all the way around it and not feel compelled because it's on an incline to go down or up the incline without friction. So there should be no motion up and down, and therefore we can say the acceleration in the up and down direction should be zero. Now that we look at it, we can say, okay, well, that means Fn sub y, the y component of the normal force, plus negative mg has got to equal zero. So this gives us equation 1, Fn sub y is equal to mg, or actually more specifically, I should have written, let me go ahead and do that. Sorry. I should have went ahead and substituted that I knew if n sub y. The fn sub y, of course, is fn cosine theta. So fn cosine theta plus negative mg is equal to 0. Now I can solve and find out that the fn should be mg, which when it's over to the other side is going to become positive, divided by cosine theta. So that's one result. Now the other part, and hopefully y'all get this, but this is the summation of forces in the x direction is equal to mass times acceleration in the x direction. Uh, the car is making this turn this way, and it's got to be accelerating horizontally to the right to make that turn. And it's moving at a velocity v, of course, so we can make use of that. So the acceleration is going to be the v squared over r, where r is the distance from basically the center of the car to the center of rotation of the turn. And we're going to work out what that is. And here's what we do. It turns out there's only one force acting in the x direction. It happens to work in the positive direction, and it's Fn sub x. So I'm going to say Fn times the sine of theta is equal to m v squared over r. That's equation 2. Okay? So now I'm going to plug equation 1 into 2. So in doing that, what I get is mg over cosine theta times the sine of theta is equal to mv squared over r. Something magical happens here. We notice, for instance, that the m cancels out from both sides, which is good because that means we're designing a banked curve that doesn't depend on the mass of the vehicle. So we don't have to have a different curve if you're driving a Prius or if you're driving a Hummer or a Mack truck, right? So that's kind of good. Now we can go ahead and solve for this, and what we get is the tangent of theta, since sine over cosine's tangent, has got to equal v squared over gr. So this is the actual correct answer, and your author expects you to use that formula over and over again. You don't have to derive it every time, but I highly recommend that you learn how to derive it just in case you need that. All right. So tangent theta equals v squared over gr. That's the formula that you ultimately get. Now, when I asked you, think about the negative consequences. Can y'all think of a negative consequence if we actually design this for like, let's say 60 mile or let's say 55 miles per hour? Can you think of a drawback to having it banked at the angle theta given by 55 miles per hour?
If you have less, would you start sliding downwards?
Exactly. Good job. Yeah, and that's what most people do when they encounter a exit ramp and that they've never been on before. They're like, slow down, right? And if you're actually like on a snow-covered exit ramp that's are more like ice-covered, and you happen to not be going the 35, which is the posted speed limit, yeah, you could literally just slide down to the inside, and exit ramps sometimes have big ponds and cliffs and all sorts of stuff like that. I hopefully they're not as steep to cause problems, but yeah, that's the major thing I was shooting for. Good job. Any questions on that? Is circumference divided by the period equal to v tangent? Oh, the circumference over, yeah, the circumference divided by the period is equal to v tangent. Which is also what we just call V when we're talking about circular revolution. Okay. Now, Daniel did have this question that he wanted me to work. So you guys are completely free to go. I think everybody's already chatted me your first and last name. You're free to go on that. I'm going to try to look for that specific problem real quick, and then I'm going to solve it on here. Come back later and look at it. Once the video is posted, it should be posted tonight, or you can stick around. Doesn't matter. But thanks for coming, everybody. And remember, y'all have a online test that's been moved. So now you have till tomorrow night at 11:59 to get it done. And you also have a face-to-face test that you're supposed to get done this week, but I'm actually allowing you up until Monday night at 11:59 to get it done. I've already made the practice test for it. You can see that as I think it's called practice test 03 underscore first F2F. So it's, for the first face-to-face test. All right. Thanks for coming, everybody. Now I'm going to look for that other
Oh,
problem real quick and work it. Yes, ma'am.
I'm sorry, really quick. I had a quick question about the face-to-face test.
Uh-huh.
Did you say that we could come to one of your in-person classes and take
Yes.
it there?
Yeah.
Okay,
On Wednesday, that's pretty much my only time, though. Wednesday or possibly the following Monday, you could do it. But other than that, that's the only times. But Wednesday, you could be there as early as 8 a.m. because that's when I come in. Uh, or you could take it at 9, you could take it at 9:30, you could take it at 10 o'clock, 11, 12. The last time you can actually take it is 2 p.m.
okay.
Okay.
I'll
You just look for me on that hall if you want to do that.
okay, great. I'll try to be there as soon as possible that
Okay. Let
day.
me know if you do decide to do that. Just, tell me that you're planning on coming that way. I'll keep an eye out for you.
Okay, great.
So
Can I
you can
just
text
text
me.
you?
Yeah, that'd
Okay,
be
sure.
best. Thanks,
Great.
Brianna.
Thank you so much. Have a great day.
You too. Thank you, Iruz. Appreciate that, bud. All right, I'm looking for it was chapter 5 that Daniel talked to me about, and that makes complete sense. But what I said, my reason for not doing it was completely nonsensical because I was thinking I was finishing up chapter 4, but I just finished up chapter 5, so I could have done yours. I'm sorry I got confused and I don't know, just did something screw up. So sorry about that. It's not the pushing the block, I don't think. Well, let's check. Let's see.
It's 5.31.
Oh, okay, cool. Thank you. Appreciate that. 5.31. Gotcha. Yep, that's the one I remember. I'm going to draw it up here real quick rather than put this on my screen because if I put it on my screen, that might be I know that's a copyright violation. So, which this probably is too, to be honest with you, but at least it doesn't, jump out at people and say, "Hey, somebody stole my crap." So, what I'm going to do is I'm drawing a surface and then you're going to have a big box on the bottom that has a mass of 5.0. I'm going to call that 5.00 kilograms. Then a rope is, whoa, Nelly, sorry. Then a rope is tied to that, goes around a pulley, frictionless pulley at that, and then the rope comes back out and attaches itself in a convenient way so that it's perfectly horizontal to a 3.00 kilogram block. Uh, 5 kilogram block. The coefficient of static friction is 0.65. So mu static is 0.65. Mu kinetic is 0.35. And what they would like to know is F minimum to 2 sig figs. And if the force is 10% greater than your answer for A, what is the acceleration of each block? Okay, F min times 1.1 is equal to F. A equals question marks, what we're looking for in that case. All right, so this one's not that bad, but it's really easy to miss things. So what we have to do is we need to draw a free body diagram for the 5 kilogram mass. So I'll say 5.00 kilograms. I'm going to have this like this. There's my mass right there. 5 times 9.8 gives me 49. And in fact, that's going to be in the downward direction. So that's 49.0 newtons that way. Uh, where is the, oh yeah, I forgot to draw where the force was applied. That might be helpful. So I'm going to say the force is this way. Uh, so with this in mind, we also have a force pointing to the right. The way I have this drawn, this right direction appears to be the positive direction. So I'll put F right here. We also have a normal force that the actual flat surface under the 5 kilograms is applying to the 5 kilograms, but we also have a weight. The 3 kilogram block is sitting on top of the on top of the 5 kilogram one. So we also have a 3 times 9.8, which is 29.4 Newton downward force. So that's 29.4 newtons downward. And that's from the 3 kilogram object's mass pointing up. Now, the other part is kind of weird. We also have a force this way that is the tension in the string. Now, since the pulley's massless, the tension in the string should be the same all along since the pulley and the string are massless and frictionless. If it had a mass, then it would take more tension on one side, for instance, to pull the 5 kilogram block than it did to actually pull the 3 kilogram block because you'd have to pull the actual massive frictionful pulley and the 5 kilogram block in that case. So that's why we're assuming the two tensions are going to be the same. Now, there is a friction force that's going to act here. We are trying to pull the 5 kilogram block to the right. So the friction force on the 5 kilogram block from the floor should actually point to the left. And this is going to be that's the friction force, and it's from the floor to the 5. So I'm going to call it F45 just to keep straight of that. Now, in addition to that, when you try to pull that box, that rope is going to cause the 3 kilogram block to pull to the left. That 3 kilogram block pulling to the left is a friction is going to cause a friction force between it and the 5 kilogram block, and in fact that's going to tend to pull the block to the left as well. So because of that, I have to put yet another friction force, which I'm going to call F from the 3 on the 5. Actually, that's reverse notation from what I told everybody. So it should be the force on 5 due to 3, and that other one should be the force on 5 due to the floor. So let me fix that too. I always try to keep my subscripts consistent. So this is the force on the 5 due to the floor. And I think that's about it for the 5 kilogram mass. You can see that probably a lot of people might miss all these different forces that could come up there. And that's normally what causes the error. Now I'm going to do one for the 3 kilogram block. And we got to remember that Newton's third law is, reality. So we've actually got to keep everything consistent with Newton's third law as well. And in this case, no force F is being applied to the 3 kilograms, but it still has, as I try to tell my students in my class, you want to go through each thing that's touching the object of mass M that you're applying Newton's second law to, and then look for the actions at a distance. So I see the 3 kilogram is only touching the 5 kilogram and the rope, and then the action at a distance is only gravity. Okay, so that's what helps me with this one. I'm going to put the mass right here. I'm going to say that the mass is 3.0 kilograms. And of course, 3 times 9.8 is 29.4. So I'm going to draw this force downward as 29.4 newtons. That's the weight of the block So therefore, that's the force of gravity acting on the block. We also have the 5 kilogram block trying to pull to the right, and therefore it's applying a friction force to the right on the 3 kilogram, and that's completely consistent with Newton's third law. So that's another good thing. So there's X, there's the Y. Now what I'm going to do is draw a friction force to the right, and this is the friction on the 3 due to the 5. Now, I also have a normal force that happens to be supplied by the 5 kilogram mass, and that points in the upward direction. So this is F normal, and I'll put a subscript 3, just like this is F normal, and I'll put a subscript 5, but forgot to label it. Okay, and I also have a tension T that's pulling it to the left. And like I said, it's a massless, frictionless pulley, so we expect the two tensions to be the same. I do have that tension pulling to the left, and yeah, that all looks good. I've got the normal force up, that's the force from the 5. I've got the friction force from the 5. I've got the tension there. I don't see anything else that could be bothering it. Mm, no, I think that's it. Do you see anything,
What
Daniel, I might be missing?
so you have the friction of 5 on 3,
Hmm.
but what about the friction when it's trying to move, like the resistive force of the 3 kilogram box as it's trying to move forward? Is that the same thing?
Yeah, that is the same thing. But yeah, you're exactly right because I assumed you were looking at the fact that I had two friction forces on the left diagram, and it seems reasonable that you might have two on the right. That was the same thing. I wanted to make sure I wasn't missing anything. But yeah, they're both counted as in F3.5, but we called it F5.3 on the other one. That's consistent with Newton's third law. Because if say the force on A due to B is equal to the negative of the force on B due to A, that's what Newton's third law is. The F3.5 pointing the opposite way as F5.3 is exactly what we expect. And yeah, as far as I can tell, that should all be what we need. Anything else you can think of, Daniel? We're going to give it a
No,
try
but
and
so
throw it
for
in.
the normal force of 5, it's going to be the weight of the 5 as well as the weight of the 3 weighing it down.
Exactly. That's going to make the normal force bigger for the 5.
Okay.
Instead of it being like 49 newtons, it's going to be more like 69 or 78.4. So yeah, good thing to note. All right, so let's do our summation of the forces. We're again assuming the accelerations in the y direction are going to be zero. So the summation forces in the y direction equals mass times acceleration in y direction. The acceleration of y we expect to be zero. This is going to give me F in 5 because that's a positive plus negative 49.0 newtons plus negative 29.4 newtons. And that should be it. Yep. And all of that's equal to zero. So the F in 5 we can actually solve for. I'm going to call this equation 1, and it should be 6078.4. Okay. Now I'm going to do the summation of the forces in the x direction equals mass times acceleration in the x direction. In this case, they want to know the minimums, what we're working at first, and that's just basically saying less than or equal to zero. We'll say the sum of the forces is less than or equal to zero, and that would make it come up to be a minimum. Okay, and I'll think about it some more just to make sure I'm not making a mistake there. It's very easy to make careless mistakes like that when you're thinking on the fly in real time. So in this case, we're going to have the forces being F. That's the force that the person's going to apply, and that's the one we want to minimize, minus T And
Would it be
then
greater than or equal to zero because you need at minimum?
exactly, there you go. That's that. Yeah, that was what I was worried about already. Is if I said it correctly. But yeah, that's a good point. So minus t and then minus f 5 4, which in principle we know what the formula for f 5, or excuse me, f5f is. I said 5 4, and then minus f 5 3. And that seems to be all of the forces in the x direction. And what we're going to say is, since we're going to solve for f as f min, like you said, it's going to be less than or equal to 0. And you'd see that f is equal to t plus, since we're talking about it being static, we have to assume the mu
Wait, what
static
about
is greater. Go ahead.
F, the friction of 3 on 5 or 5 on 3?
Thank you. That was the one we forgot in the other side. Good job. No, no, the fiction of 5 on 3. That is drawn here on the right diagram, but it's not drawn on yeah, it's drawn on the left too. So yeah, I did take that into account. Make sure I don't
Oh,
miss anything.
so the friction of 3 on 5 is the same as on the right diagram, the friction of 5 on 3.
Exactly. That guy corresponds to that guy. Does
Okay.
that make sense?
So I get it from a practical sense, but why did we draw it if we're not going to include it in the math?
Oh, we're definitely going to include it. We've got to do four equations of motion, the Newton's second law. I'm just doing the first two, and I can't, for instance, I got a T in there. I can't do anything until I attack this other side. We just haven't done it yet.
Okay.
Okay. Yeah, you're thinking right. So what I'm doing is I'm imagining the friction forces being at their maximum. That allows us to figure out the minimum force, because you have to be able to overcome the maximum. So that's mu s times the normal force. And if I had my actual marker going, that'd be better. So that's mu s times the normal force. In this case, this was the force on the five. Oh yeah, so this is Fn5 that we're talking about here. And then plus mu static times F5 3. So this would be the force on 5 due to 3. That one has a normal force of Fn3. So what we're saying really is this has got to be equal to, greater than or equal to those sums, but we can't do a thing with it yet until I do the F equals ma on the right hand side. So, yeah, good that you were paying attention though, because I'm not sure. Even sometimes late at night once we've been working, it's there's some chance that I'm going to make a careless mistake, like completely forget half the problem. Again, we're going to go with the acceleration in the y direction being 0. This diagram's a lot easier to deal with, though, so we can do Fn3 plus negative 29.4. I'm being very pedantic about this to make sure everybody realizes we're adding all the forces. It's just some of them point in the negative direction. So Fn3 plus negative 29.4 has got to equal 0. So now we've got equation 2, which is Fn3 is equal to 29.4 newtons. And we're going to make use of that as well. I should have labeled this one already, but I'm going to go ahead and label it 3 now. That way we can use it. Now I'm going to be the summation. I'm going to do the summation of forces in the x direction is equal to mass times acceleration in the x direction. In this case, we're again doing the same thing. We're trying to assume that the acceleration is going to be the bare minimum. So let's see what can happen. I might not even need it too much. I'll write it out either way though. So we've got the F35, which in principle would be, well, I shouldn't do that until I know the minimum, but it's F35 plus negative T is equal to m times a, which we're going to assume to be 0 in a second. So there's just no reason to put less than or greater than or anything on it. So I'm leaving that to be for right now. But what we can do is now I can plug in equations 1 and 2 into 3. So plug 1 and 2 into 3, and we get f is greater than or equal to t plus 0.65 times f in 5, which we found was 78.4 newtons. And then we found plus 0.65 times 29.4 newtons. And then that's it. So I can make this a little more straightforward, and I'm going to combine it with that last equation we just made so that we can get rid of the t. But 0.65 times 78.4, that's 50.96. And 0.65 times 29.4 is 19.11. So if I add 19.11 plus 50.96, I get 70.7. So what I'm going to get is T plus 70.7, or zero point zero 0.07, excuse me, newtons. So F has got to be T plus that. Now, here's the cool part. If we set the acceleration of this one greater than or equal to 0, we could say, I'm going to write it in red so it stands off a little better. F35 plus negative t is greater than or equal to 0, then we could call this equation 4, and we could combine it with this, which I call equation 5. So combine 4 and 5. What I mean by that is I'm actually going to add these two together because I have a positive t in this one and I have a negative t in that one. So that can actually cause the actual t's to cancel out. Let me see, do I want to do it that way? I can. It would probably be better if I did it from this side because here you see f and then minus t and then well, no, that don't work either. Okay, we'll do it a different way. We are going to combine them, but what I'm going to do is I'm going to replace t with f35 because it looks like from this equation right here that t f35 has to be greater than or equal to t. F35 looks like the way I have it written here, it must be greater than or equal to t. So I can put in the t. And actually, did we find the
And
F3.5?
substitute it in equation 5. Is that what you're trying to do?
Yeah, I'm going to put it in equation 5, and that should do it. Yeah, I think that works. So let's try this out. We'll see what happens. Uh, I'm going to now say that F, so combining this and this, I'm going to say that F should be greater than or equal to the F35 we found was the friction on 3 due to 5, and that was mu static times the 29.4. So that's the 19.11. So I'm going to say 19.11 newtons plus 70.07 newtons. And if I do that plus 19.11, that gives me 89.18 They're asking for two sig figs, so I'm gonna call that just plain 89. Let's see if that works. That was right. So despite the the scares that happened in there, everything worked correctly with that one. Does that make sense to you, Daniel?
What was your final answer again?
I got 89.18. I actually should write that down here. Uh, which equals 89.18.
Okay, yeah. I accidentally put 0.065 for the last one for F35, but yeah, I
Gotcha.
got that.
All right. So that's pretty straightforward. It's not, well, I shouldn't say it's straightforward. It's sort of straightforward in the sense that you know what you got to do, but it's just got so many different parts that you might forget a force. Other than that, it's not terrible. The good news is the second part, you don't have to worry about less thans or equal to. You're just literally trying to see, is the force big enough to make any acceleration? And then if that's the case, what is the acceleration? So we've already accounted for instance, the force being 89.18. So what they want you to use now is let F be 89.18 times 1.1, and then calculate it not with the coefficient of static friction, but with the coefficient of kinetic friction. So you're just going to take everywhere where you saw mu sub s, you're going to replace that with the mu sub k, which is 0.35. Does that make sense?
Yeah, I didn't have a problem with the second part of it. It's
You
just I
did?
didn't get to the right answer on the part one.
Okay, gotcha. Oh, so
But
you said you didn't have a problem with part B, and it was just more of a problem with part A?
yeah,
Okay,
and
cool.
then once I got it wrong so many times, it gave me the right figure, and then I just was able to like reverse engineer it for
How'd you get it
part
the other?
B.
Yeah, there you go.
But yeah, I think it was the the friction force of 5 on 3 that threw me off.
hmm It's
And then I
easy to get
wasn't
those mixed
100%
up.
sure if I was counting the weight of 3 on 5 for the normal force of the 5 kilogram.
Yeah, it seems weird, and yeah, in that case, you got to realize that the what's a weight in one case turns out to be a normal force in the other case. So yeah, the 29.4 turns out to be the FN3 later.
Actually, no, I think I had the friction force of 5 on 3. It was just when I was doing the free body for the 5 kilogram,
hmm
I didn't account for the resistive force of the friction of 3 on 5.
Oh, gotcha. Cool. Well, hopefully this was good enough to help you out on that.
Yeah, yeah,
Anything
thanks.
else I can do for you?
My only other questions were on the bank track, but we did that at the end of the lecture, so I'm good.
Oh, okay, cool.
Yeah,
Yeah, that
thank
should
you.
be pretty straightforward. And they do want you to use that formula over and over. You'll see in the examples that the book gives you. So it's pretty normal. But I'll be posting some more videos of other problems from chapters 4 and 5 too, probably. So keep an eye out for those.
Awesome. Well, thank you so much. Have a good night.
You're welcome. You have a good one too. See you, Daniel. All right. Looks like we are done. Bye bye. Bye bye.